Hello, calculus fans. Let's take a curve, y equals x cubed, so just an everyday, ordinary, average cubic function, and we'll say the x values are going to go between 0 and 2. And they're going to take this curve and revolve it around the x-axis to generate a surface of revolution. Let's do two things here. Let's find a parameterization of this surface, and then we'll use that parameterization to find a surface area of S. So this is a surface of revolution, and we've talked about the general form of parameterizing such surfaces. In general, if we take a curve y equals f of x and we revolve it around the x-axis, then we get what I would call the standard parameterization of such a surface. It looks like this. Our parameter variables will be x and theta, so it's going to be x, f of x cosine theta, f of x sine theta. So the theta is measuring something about revolving around an axis. The x values, of course, stay between a and b, and the theta values going around will run from 0 to 2 pi. So in the particular case we're dealing with, here's the parameterization I think we want to deal with. We'll say that r of x theta is x cubed cosine theta, x cubed sine theta. And as we said before, the values of x go between 0 and 2. The values of theta go between 0 and 2 pi. All right, we've got the parameterization. Let's now find the surface area. So we've computed a couple of derivatives, Rx and R theta, and then we need to cross them. So I went ahead and did the cross product. This is something that you could do in MATLAB, or you could work it out by hand. I'd like to spare you the details of the cross product. Now we need to compute the length of this cross product. It's going to be the square root of 9x to the 10th plus x to the 6th cosine squared theta plus x to the 6th sine squared theta. And you should notice that this expression here, the x to the 6th cosine squared theta plus x to the 6th sine squared theta, we can factor out x to the 6th, and then what's left over is just 1. And then a little bit more algebra, and we wind up with this final expression here, x cubed square root of 9x to the 4th plus 1. So you should verify the algebra that's in here. All right, now we're ready to compute the area of S. All right, so we're going to compute the area. It's the double integral over d of the length of Rx cross R theta. And so when we write this down as an iterated integral, we'll get the integral from 0 to 2 of the integral from 0 to 2 pi of x cubed square root of 9x to the 4th plus 1 d theta dx. It's a nice integral. The bounds of the integral are all numbers. There's no theta inside the integral. And that means when we integrate from 0 to 2 pi, we just end up getting the 2 pi, which we'll factor out. And now we can evaluate this integral using a substitution. We'll let u be equal to 9x to the 4th plus 1, which makes du 36x cubed dx. We don't have 36x cubed dx, so we'll divide out by 36. We'll change the limits of integration by plugging the 0 and the 2 back into the u. And we end up with a fairly nice integral like this. The number's a little bit messy, but the computation is fairly straightforward, and we end up with pi over 108 times 145 to the 3/2 power minus 1. You can verify the computations that have been done here. Okay, that's all for now.